It's time to start, I guess, right? Well, today I'll prove you, I'll give you an application of Wasper Theorem. Well, it's estimate for its lower estimate for so-called rank of the diagonal form. So well, what is diagonal form? Definition. F, the function f, is a diagonal form from the P to the P. The P, no, the P in the N. To the P. If f is representable in as f x1 xn equals to c1 x1 in the K, c2 x2 in the K, cn xn in the K. Well, this is all the functions of this form. Well, rank of a diagonal form f x1 xn is well, c1 x1 in the n, cn xn in the n, in the k. Right. Where not all of c1 cn are 0. Not all. So this is not well. If a function which is constant 0 is not a diagonal form, right? Rank of the diagonal form, its image of the n, size of the image. So is rank of f, which is size of c1 x1 k ck cn xn k whenever x1 xn are in the P. Well, its image. Its size of the image. Good? Cardinality, right? Size, cardinality. Well, our aim for today is to prove the theorem well, there will be only one theorem for today, so without number theorem. Suppose f of x1 xn is c1 x1k, cn xn in the k is a diagonal form. Then rank of this diagonal form is at least minimum between this 2n minus 1 by p minus 1 from zp n onto zp, right? So p in here divided by do you understand what is this? This notation, do you understand this notation? This one, brackets. What is this? GCD. This is GCD of greatest common divisor of k and p minus 1. GCD, greatest common divisor of k and p minus 1. And p, well, where k brackets k and p minus 1, it's g c d of k and p minus 1. I won't write this GCD. Greatest common divisor. Well, it's our aim. First lemma. It claims, suppose f x1 xn is c1 x1 in the n, the k cn of xn in the k is a diagonal form right? From ZPN to onto ZP. I'm sorry. Well, and suppose that k is divisible by p minus 1. K is divisor of p minus 1. We get rid of this supposition a bit later. In the first lemmas, we always suppose that k is divisor of p minus 1. Well, right, then rank of the form f, it's equal to 1 modulo k. Do you understand what? Do you understand the statement? It's 1 modulo k, right? Well, no, well, K is divisor of P minus 1, but nevertheless, rank is 1 modulo K. What again? So? Yeah, that's how we get rid of this instead of, well, we put here GCD instead of statement, instead of supposition that K is divisor of P minus 1. Right, up to. Yeah, it's cardinality. Well, we need the GCD because we need this to be this to be divisor of P minus 1. So this is whole number because K GCD of K and P minus 1 is divisible by P minus 1. That's our replacement for K actually. The GCD for common case, for general case. So that would give us the cardinality. Well, actually, yeah, it's minimum cardinality of ring in its structured case, so-called. Well, okay. Now, first, let's show that it's 1 modulo K. Okay. Proof. Well, let's denote. AK is X in the K whenever X is from CP without 0. AK star. AK star. Well, AK star is subgroup of ZP without 0. It's a multiplicative subgroup, right? Do you know that? Is a multiplicative subgroup of ZP without 0, which is group on the multiplication, right? Do you understand why? How to check that this is subgroup? We have to check that if we take 2 elements of subgroup, product of 2 elements is inside subgroup, it's easy to check that. 0 of the group in this, in our case, it's 1, right? Because subgroup is multiplicative subgroup. 0 of the subgroup is 1. 1 is inside. 1 is really inside. 1 in the K is 1. And if we suppose that X in subgroup, then X inverse in the group is also. Well, if X, Y is representable in the form X in the K, then Y minus 1 is representable in the form X minus 1 in the K, which is also inside subgroup, inside a K star. That's why, by the way, we removed 0, because we cannot invert 0 modulo P. Well, all the invertations we make inside ZP, right? Okay, what is the size of the subgroup? Well, naturally, it's divisor of the size of the group, which is divisor. This must be divisor of p minus 1. Actually, this is p minus 1 divided by k. That's why we need k to be divisor of p minus 1. Why this is true? Why size of this subgroup is this? Remember this fact that the multiplicative subgroup of ZP is cyclic group, right? So we have generator of this cyclic group. Do you understand, Diego? G is generator of ZP without 0. Then AK star is this one. It's G in the power of 0, which is 1, G in the power of k, G in the power double k, till G in the power of what? Of p minus 1 divided by k minus 1 by k. Well, because if we take p minus 1 divided by k multiplied by ka, this is p minus 1. G in the p minus 1 by Fermat-Small theorem, it's 1 modulo p, right? So we repeat. We start repeating. All these elements are representable in the form some element in the kth power. All the others elements are not representable, but I won't prove it, but, well, okay. Let's use it. So that's why size, cardinality of AK star is p minus 1 divided by k. If k is not divisor of p minus 1, then size of the subgroup, it's p minus 1 divided by this, but we will prove it a bit later. Well, let's continue. Let's continue. By the way, I looked through my previous year lectures and found that I'll follow this course I took in previous year. So this is quite adequate for this stream, for the students' program. So probably I cannot, well, in previous year I took in average about 2 hours per lecture. So in average lecture was larger than 1 hour 20 minutes. So probably I cannot cover everything from previous year, but I'll follow this course. Again? Well, you mean program from previous years, no?
No, for this course, we need to know group theory.
Group theory, you don't need actually, but you need to know basics of group theorem. Theory, well, about generators, about cyclic group, about the fact that probably subgroup is size of subgroup is divisor of size of the group. So you need to know the basic facts actually. We will use groups here, and later later. I go straight to graph theory. So probably I found out that graph theory is more pleasant for you, so I just give applications of graph theory to additive combinatorics. That's most pleasant for students, English students material, so I just selected these topics. Okay. So we finished groups today, I believe, if we finish this theorem today. Okay, right, AK star is this one. Well, what next? Next, what about range? Range is size of this set. C1 AK star, right? Plus C2 AK star plus so on and so forth. CN AK star union 0. We removed 0 outside from this set, so just the image. It's actually, what is the image? We substitute all the xi's from ZP without 0, and we get AK star on each position, right? So this is size of the sum set plus 0. Right, let's prove that size of this sum set is divisible by k. Well, modular, not k, sorry, not k, p minus 1 divided by k. Divisible by p minus 1 divided by k. Well, how to prove it? Okay, let's prove this fact. AK star multiplied by the set of C1 x1 k Cn xn in the k x1 xn in the k. We multiply this set by this set. Well, let's denote it somehow. Well, A of f of something. A of f. It's set, it's image, right? It's subset of A of f. Let's prove it. Well, let's take any y from AK star. This means that there exists x from ZP without 0, such that y is x in the k. Let's multiply y by A of f, right? This is x in the k by A of f, right? Which is set C1 x in the k x1 in the k, Cn x in the k by xn in the k, x1 xn in the p. But this is subset of AF, right? Because this is element x by x1 in the k, right? This is x by xn in the k, so this is subset of AF. So which proves that AK star by AF is subset of A of F. Right. So, what does this mean that a subgroup A of F multiplied by AF is subset of AF? This means that AK star is part of symmetry subgroup, right? Remember we had symmetry subgroup of set. It's set, it's all the elements. Remember we had this sim of A notation. It's all the elements of the group such that if we add element to the A, we get the set A, right? In our group ZP without 0, we have to replace addition by multiplication, right? Because it's multiplicative group. So AK star is subset of symmetry subgroup of AF. Probably it's entire symmetry subgroup, but it's at least subset of symmetry subgroup of AF. Right. Remember we proved that AF is union of cosets of the symmetry subgroup. So AF is union of cosets of AK star, but cosets in ZP without 0. So, which means that AF without 0, because we have to put everything inside this group. 0 is not inside the group. So F is without 0 is a union of cosets of AK star, which means that AF without 0 is divisible by sides of AK star, which is P minus 1 divided by K. So AF without 0, sides of AF without 0 is 0 modulo P minus 1 divided by K. Right? And this means that if we add 0 inside, it's 1, this modular. Size of AF is 1 modular P minus 1 divided by K. That's all. Right, next lemma. Next lemma. Yeah, F with 0 is 1, right? Because F without 0 divisible by P minus K, P minus 1 divided by K. So F with 0 is 1 modulo P minus 1 divided by K. Okay, lemma 2. Suppose A subset of ZP ZP or ZP star. I don't quite remember that. Right. Yeah. Size of A is this. And S is between 1 and p minus 1. So it's not one element set, it's not p minus 1 element set. Right. Then, if sum for A inside A of all the elements of A is 0 and sum of squares of all the elements of A is also 0, then A is not an arithmetic progression. Well, suppose, okay, let's prove. Suppose A is an arithmetic progression. A is an arithmetic progression. So A is A0 plus ID whenever I goes from 0 till h minus 1. Well, as far as we know, sum of all the elements of A is 0. So which is? I mean 0 modulo P, naturally. And now this is also 0 modulo P. Right. This sum is 0. And this is sum for I.
Do you need 0 or P? Why?
0 modulo P. Like this. Right. Sum for I, A0 plus ID. Right. Well, this sum is A0 by S, right? Plus sum for D by sum for I from 0 till S minus 1, I. This sum is what? Is it's sum of arithmetic progression. So this is A0 by S plus D by S minus 1 half. So this is 0 modulo P. Right? So S is not 1, is not 0 modulo P. So we can state that A0, we can cancel this S, right? We can multiply by S inverse. And S inverse is 1, so we can remove this S. And so A0 plus D by S minus 1 half is 0 modulo P. Good. Good. Next. Good. Now, sum for its 0 modulo p, which is equal to sum of A inside A square. Right, which is sum for I 0 to S minus 1. A0 plus ID. Where? So this is sum for I from 0 to S minus 1. A0 square plus double ID plus d I square d square. So which is S A0 square plus double d by sum of I till S minus 1 of I, which is S minus 1 half, right? Plus d square by sum of I from I0 to S minus 1, I square. This sum is equal to this one. To this one. All right. Well, from this we have that A0 is minus d S minus 1 half modulo p. Well, let's substitute it in here. So this is S minus 1 half S minus 1 square by 4 by d square. Right? That's good. Okay. Plus double d plus d S minus 1 plus d square S minus 1 double S minus 1 by 6. So sorry, I forgot. Oh, this is A0 here. So we have to substitute it in also in here. So this is minus double g square by S minus 1 square by 4. Right? Well, this is half. So, what do we get? We got that that it's d square by S minus 1 by double S minus 1 by 6 minus d square by S minus 1 square by 4, right? Is correct? Well, what is this? This is d square by s minus 1 by double s minus 1 by 6 minus s minus 1 by 4. What is this? This is d square by s minus 1 by 8s minus 6a, which is double s, 4 plus 6, so minus 4 plus 6, so this is plus 2 divided by 24, right? So, well, this is d square by s minus 1, s plus 1 by s minus 1 by 12, So this is 0 modulo p. Well, look at this. Look at it. Is it true? Cannot be true? Look, if it's 0 modulo p, this means that either d square is 0, but in this case, A is one element set, and this is forbidden, right? If this second part is 0, this means that what? This means that what? Either s is 0 or s plus 1 is 0.
Well, s cannot be 0 and 1, so d must be 0.
Yeah, s cannot be 0 because s between 1 is strictly greater than 1 is strictly smaller than p minus 1. So this part is not 0. And this part is must be 0, but this cannot happen. So our supposition is false. Contradiction. So, okay. Good. Next lemma. Well, lemma 3. Suppose AK is all the x in the K whenever x is in ZP. So this is AK star I union 0, right? Let's just introduce this notation. So, well, what we need to know? We need to show that if K is between 1 and strictly smaller than P minus 1/2, then AK is not an arithmetic progression. Well, proof. How to show that? Well, let's check these two conditions. Look, these conditions are true because, well, because size of AK is what? Well, forgot. Suppose Pk is divisor of P minus 1 actually. Also, we work under this supposition. I forgot this. And AK is this one. Well, look, size of AK is P minus 1 by K plus 1 with 0. What can we say about size of AK if K is this one? So yeah, this is AK is at least 3, right? Because because K is strictly smaller than P minus 1/2, so P minus 1 divided by K is at least 3, so it's strictly greater than 3 even, right? And strictly smaller than P minus 1/2 plus 1. Because, well, look, P minus 1 divided by K is strictly smaller than P minus 1 divided by P minus 1 by 2, right? So which is 2? Strictly greatest, sorry. So it's at least, but plus 1, it's 3. Right. So K is at least 3, at most what? P minus 1/2 plus 1, which is P plus 1/2. When this is strictly smaller than P minus 1, when? When it happens? When P is strictly greater than 3. Good, right? So, yeah, P is at least 5. We need this. Yeah, that's our limitation here. Look, okay, so size is, this is strictly smaller than P minus 1. So we have our conditions on size of A. We have to check this and this. Good. Remember, I wrote you this. AK is AK star union 0, but AK star is generator in the 0, which is 1, generator in the K, generator in the P minus 1 divided by K minus 1, right? Good. Then sum for A inside A, K, sum of all the elements of AK, it's sum for I from 0 till P minus 1 divided by K minus 1, G in the I, which is, it's sum of geometric progression, so it's G in the P minus 1 by K minus 1 by G in the 0, but G minus 1. Well, under these suppositions, this is not 0. Because this is 1, this power is 1 whenever P, this power divisible by P minus 1, right? So this is not divisible by P minus 1, we check that. So it's not 0. It's not 0, modulo P. Sorry, it must be 0. Sorry, 1 minute. It must be 0. So by K, and this is 0, right? Because this is 1. Because denominator Ki, so Ki. So this is 0 modulo P. By small format theorem, right? And here, let's check this condition. Let's check this condition. Sum for A from A square. This is sum for I from 0 to P minus 1 and by K minus 1. G in the double I K. It's also sum of the geometric progression, so which is G in the double K P minus 1 of, no, P minus 1 divided by K minus 1 by G double K minus 1. And here G in the K minus 1. Right, but this is 0, right? Because by Fermat's small theorem, this is 0. No, this is 1. G in the power double P minus 1 is 1 modulo P. So, by lemma 2, A is not an arithmetic progression. AK is not an arithmetic progression. Unfortunately, when K is equal to P minus 1/2, this is exactly arithmetic progression because, well, look, this AK looks like minus 1, 0, 1. There are only 3 elements inside. So, but minus 1, 0, 1 is arithmetic progression. So when K is equal to 1, then this is entire ZP, this is also arithmetic progression. So we cannot remove anything from here. Okay. Well, next. Well, now lemma 4. Yeah. Lemma 4. Which claims what? Well, this is lemma about situation when k is not divisor of p minus 1. Well, suppose denote, let's denote S as not S, D as greatest common divisor of k and p minus 1. Then AK star for general case, AK star is AD star. Well, simply like this. So these sets are equal, so we can replace this k by GCD simply. Right? Is there any limitations? Well, no. Proof. Okay, good. Well, let's return to our generators, right? Look here. This inclusion AD is subset of AK star. It's simple. It's simply. Look. All right. Let's take any. Any x from y from AD star. Well, then there exists f from ZP star, ZP without 0, such that y is equals to x in the D. But D is divisor of p minus 1, right? Right? And also D is divisor of k, because it's greatest common divisor. Right. So D is divisor of k, so there exists D is k by G. So which means that no, k is dt. Converse. I'm sorry. AK subset of AD is easy part. So it's in AK. Well, it's K, which is X in the DT. So which is X in the D, in the T, in power of D, which is element of a D star. So which means that AK star is subset of AD star. Inverse inclusion. So AD star is subset of AK star. how to prove this one? Well, y is inside a d star, which means that there are x from zp without 0, such that y is equal to x in the d. Well, but d is GCD of k and p minus 1, remember? And there are fact that GCD, greatest common divisor, is always linear combination of k and p minus combination of common divisor of a and b is combination of a and b, right? So d is equal to k by L plus p minus 1 by t, where L, T are whole numbers. Do you remember this fact? Huh? Do you? This is main fact from Euclidean algorithm, actually. It falls from a Euclidean algorithm of counting greatest common divisor. We can get this combination from backwards when we move backwards the Euclidean algorithm, actually. Well, let's take this. So greatest common divisor is representable in the form KL by p minus 1 t, p, l, and t whole numbers. Okay. Oh, this means y is x in the d, which is x in the k l by x t in the p minus 1, right? So this is one modulo p. So this is equals to x in the L in the k modulo p. But this is element of a k star. Well, inverse inclusion is proved, so these are equal sets. I just took star set. Well, we can prove the same for non-star set, because, well, AK is differs from AK star by adding 0 inside, right? So if we have the same set here, AK and D also the same set. Okay, so this lemma shows us how to use, work with a case when k is not divisor of p minus 1. We have to replace this k by this greatest common divisor, and nothing changes. Well, proof of the theorem. I forgot. Well, 1 minute. I forgot some limitation inside the theorem. Yeah. P is greater than 3, so it is 5. Prime number. I didn't write these limitations, and well, K whole numbers such that natural number such that 1 is greater than. Look here. We take bounds from here. So it's but k, we replace k by k GCD k p minus 1. So we need these two limitations from this lemma. P is at least 5 and k is this one. Then for any diagonal form, f, which f from x1 xn, which is c1 xn x1, and k cn xn in the k, range of this form is at least minimum between 2n minus 1 by p minus 1 by GCD of k and p minus 1, well, plus 1 and p. Right. Okay, let's prove this. There. Proof of the theorem. Well, induction by n base of induction. Well, n equals to 1. Whenever n equals to 1, the range of the form is size of AF, AK, right? AK. Which is size of what? Remember, by lemma 4, which is, this is size of what? Of AD, whenever D is K, and GCD of K and P minus 1, right? Well, but size of AD is P minus 1 by D plus 1, right? Substitute here n equals to 1. It's P minus 1 by GCD plus 1, right? Moreover, by this according to these conditions, this is not greater than P. It's even smaller than P minus 1, actually, right? So this is equal to minimum between 2n minus 1, P minus 1 by GCD and P. Right. Inductive step. Here, actually, well, this is a place when problems appears. Look, let's write this form as C1 x1 in the k, Cn minus 1 x1, xn minus 1 in the k plus Cn xn in the k. If this form doesn't depend on xn, then nothing changes, right? We can use just supposition of induction. If Cn is not 0, this is something we have to prove. Well, well, the range of the form, this is cardinality of the union of two sets, right? No, it's cardinality of sum of two sets. Its first set is C1 x1 in the K, Cn minus 1 xn minus 1 in the K whenever x1 xn goes from Zp. Right? Plus, plus set Cn by xn in the K whenever xn goes from, we'll take it from this. It's sum of this, size of this sum set, right? By, let's denote this B, and this is A. Look, here, we can use Cauchy-Devan port, right here. By Cauchy-Devan port, it's at least minimum between A, size of A, plus size of B minus 1, and P. Size of A, lower bound for size of A, it's 2n minus 3 by P minus 1 by D plus 1, right? Plus size of B. We can count this size of B. What is this? It's AK, right? So the size of AK is this one.
What is the size of B again?
It's size of AK, right? It's size of AK. Okay. And we have a problem here. What kind of problem? Do you see it? We haven't proved the inductive step because Cauchy-Devan port doesn't give us the required bound. We have to obtain this bound. But we obtain 2n minus not 1, but minus 2 by P minus 1 by D plus 1 and P. We have to improve this bound from Cauchy-Devan port. That's why we need Wasper theorem. Well, we have to show that this lower bound is not attainable. It cannot be attained. So in order to do that, we use Wasper theorem. Suppose a range of a form is equal to minimum between, not minimum, well, simply equals to 2n minus 2 and P minus 1 and D. If minimum attained by on P, there's nothing to prove, right? In here. If this 2n minus 1 by P minus 1 divided by D is larger than this, if this already greater than P, then everything shows. So we have to suppose that this is strictly smaller than P. Range of form plus 1. I forgot about that. We suppose that this is strictly smaller than P. Otherwise, we proved everything right. Well, which means that since range of the form is size of A plus size of B minus 1, which is size of A plus B, right? We just get that AB is critical pair. So, which means that AB is critical pair. It's not ZP, A plus B is not ZP, and lower bound is attained. Is a critical pair. Well, by Wasper Theorem, there are strict classification of critical pairs. Well, first, then, one of three cases takes place. Well, first case, minimum between A and B is 1. This is impossible. Why? Why this is impossible? Because of the conditions, at least. Because of the conditions of theorem. Look, B is at least a 3-element set, right? A is also at least 3-element set because it's some set of sets which are also each of this set is also at least 3-element set. So this is at least 3, which is at least 3 from conditions of theorem. By conditions of theorem. Of the theorem. Second, case, it's A, there exists C from ZP such that A B is C minus A C minus A forget this word complement, right? Thank you, complement. C minus A complement. Why this case is impossible? Just because range of the form is because say size of A plus B. But in this case, A plus B is exactly, has cardinality exactly P minus 1, right? This is the specific case when A plus B in size is P minus 1. Right. Why this is impossible in our situation? Because by lemma 1, range of the form is 1 modular P minus 1 divided by D, right? By lemma 1. But P minus 1 is not 1 modular P minus 1 divided by D. It's 0 modular P minus 1 divided by Z. This is contradiction. Well, but and also this P minus 1 divided by D is at least 3, and at, well, not at least 3, at least 2. Well, yeah, it's greater or equal than 3, and smaller or equal than P minus 1 half. So that's why 0 and 1 are different residues. Right. Well, this case is impossible. Third case. The third case in Wasper theorem is claims that A and B are arithmetic progressions, right? Arithmetic progressions with the same difference. Why this case is not possible? Remind lemma 4. By lemma 4, AK is not an arithmetic progression, but our B is a shift of AK. So by lemma 4, AK is not arithmetic progression by lemma 4. So, but by lemma 4, lemma 3? Lemma 3. Lemma 4, it's AD equals AK, right? Lemma 3. B is not an arithmetic progression. So, none of 3 cases from Wasper theorem is not hold, are not hold. So this means that we have strict bound in here, but also range of the form is multiple of P minus 1 divided by D by lemma 1, right? So this means that range of the form is strictly greater than minimum between 2n minus 2 by p minus 1 by d plus 1 and p, right? And since by lemma 1 range of the form is multiple of range of the form is one modular p minus 1 by d. Since a range of the form is strictly greater than this, it at least greater bar by p minus 1 by d. So range of the form is at least minimum between 2n minus 1 minus 2 by d by p minus 1 plus p minus 1 by d plus 1 and p. So, and this is what we want to show, right? This is our bound. We add here 1. This is everything we want to prove. So we finished.